My name is Nassim Haramein. Thanks for coming, all of you. We've got people from everywhere. Portland, Ashland, Reno, all the way from Reno. It's great. Thank you all for being here. So today we have a big day. A lot of information is gonna flow through this room today, and we're gonna go through all the physics from universal size object right down to subatomic particle, going through consciousness, ancient civilization, chemistry, biology, and so on. So we've got a big agenda. It's going to be fun. And it's going to take a little time. So be comfortable. Make sure you are comfortable. Make sure you have enough water to lubricate your brain. Lubrication. And make sure that if you have to that you eat enough and all this, so your blood sugar doesn't drop too far. Sometimes I see people, I see smoke starting to come out of the ears. Then I know there's like damage being done. So we'll try to avoid that today. Oh, okay. Maybe we can turn that down on the board. Which one is that? That one there? Low. Okay. Is that better? Yeah. Good. I've been having a little bit of trouble with my throat, so usually I just project, but today I'm going to try to be nice to my voice. Yeah. Get good lubrication going. So, go ahead.
What's the break schedule?
The break schedule is when I see everybody's turning purple because they have to go to the washroom and stuff, then I'll stop. Actually, if you guys are really exhausted and you need a break, just let me know, because I just keep on going. I just go and go for like 13 hours. So, sometimes I forget about the crowd. And so, oops. So, but in general, I'm going to try to break around 1 o'clock or 12:30. And then we'll reconvene for a little more, and then we'll have lunch around 2, and then come back and then I have the evening sessions. We might be here for a while. So I was asked to present a bunch of different things today that I usually don't have time to present, so I'm going to try to squeeze it in. So especially a section on the Knights Templar that I usually don't present. So I'm going to talk real fast. One thing that happens is that when I'm presenting this information, there's a certain amount of complexity. Although the concepts are really simple and you're going to get them right away, there's a certain amount of complexity. There's a certain amount of rewiring that occurs from things that you've been taught and from just a new way of thinking coming in, and that takes a little bit of time. And what happens is that if you have too many questions that are unanswered, then it starts piling up, and that's when I start noticing people turning white, and it's like, oh my God, they're gonna explode. And so because it makes like a dam of all the things that are not figured out. So I'm going to allow you to interrupt me and ask questions, but it's gonna have to be like really, really crucial for you to interrupt me and ask questions. Otherwise, you know, I just get interrupted too much and it breaks the flow and it's really hard to get all the information in. So before you ask questions, please think about it or see if I'm going to answer that question shortly after, because commonly that happens. But if it's really piling up and you just cannot go forward in the thinking without getting those questions answered, please just interrupt me. You can start screaming, you know, jump up and down or something. I'll get the signal. So I'm going to go through the information today in a little bit of a chronological way. How I came up with it and how it changed my life and how my life evolved as the information evolved. And you'll see that although this information can get extremely complex extremely fast, the way I learned about it, the way I learned it, makes it easy because it was just a series of logical progression that I teach typically to even 7 years old. And actually, some of the 7 or older kids commonly after the talks come up to me and say, "Are you sure the other physicists don't think this way?" And I'm like, I really checked it out. I spent 20 years checking it out. They really don't think this way. And it boggles their mind because it's kind of obvious and it's kind of instinctive. It's not kind of instinctive, it's instinctive. And funny, it's a funny thing that like commonly now, they think of these thoughts as counter-instinctive. But I think they're quite instinctive. And they got counter-instinctive as a result of confusion. In the early ages, when we learned some of the foundations of our reality at school. So that's really what happened. At the age of 7, I had a bunch of esoteric experiences. And we're not going to get into that, but I had an intuition, and I definitely had experiences that told me that there was something else than the reality we observe. That like the reality we observe is just like a little bitty part of what's going on. Just like if you'd like the electromagnetic spectrum has a section that we see, and then there's a whole bunch we don't see. And the part that we don't see has huge impact on the physics of the part that we see. And I felt that very early, you know, until they discovered, for instance, X-ray and infrared and long wavelengths and so on. They thought that all there was the visible spectrum. And, you know, it became clear later on that there wasn't, that there was much more. And I think that it's becoming clear now in current physics that there is a whole bunch of stuff going on that we're not aware of that is actually generating the part that we are aware of. So when I was 7, I noticed this. I had experience that made me notice this. So when I got to the age of 10 and I got into my first geometry class, and the teacher went to the blackboard and said, "Today we're going to learn about dimensions," I thought, that's it. Oh my God, finally somebody's going to explain to me what's this other world about. You know, these other dimensions that I felt were present. And I got really excited. I was like, oh my God, finally an adult that's going to talk about something real, you know, and something that makes sense to me. So the teacher started the lesson and I got really, really disappointed. He didn't tell me anything about the dimensions that I was experiencing earlier on in my life. But he actually gave me one of the major keys to the evolution of this theory and to its conclusion and into its proof that is now being peer-reviewed in many universities around the U.S. and from scientists that are looking at it from NASA and so on. So it's really exciting. And that, at the age of 10, made a huge difference. What the teacher did is he went to the blackboard, and we'll call this our blackboard today, and he made a dot. And he said, the dot is dimension 0, and it doesn't exist. And I went, okay, I can see it, but it doesn't exist. And, you know, I was near the door in the back of the room. I was always closest to the door because I was having so much problems at school. And, you know, I'm like, okay, whatever, you know, if you got a dot that doesn't exist, I can go with that for now. And then he said, this is a series of dots that he placed together and made a line and said this is dimension 1 and it doesn't exist either. It still doesn't have volume. And, you know, that seems consistent to me. Then he placed a bunch of lines that are made out of dots together, made a plane, called it 2D, and said this is the dimension that you live, that your comic strips lives in. It still doesn't exist. It still doesn't have volume. Well, until then, although, you know, it was kind of a bizarre approach, it was consistent. But then he did something that seemed like a miracle. He grabbed 6 of these planes and put them together on the blackboard, made a cube, and said, this is dimension 3, 3D, that one you exist in. And I was in the back of the room, and I'm like, oh my God, how can that be? And I could tell that all the other kids in the room were like, huh? You know, but nobody was saying anything. I wasn't about to put my hand up because I knew the next thing that was going to happen is the door was going to get open and I was going to get kicked out again. So I didn't want to do that. So I didn't say anything, but it didn't make sense because it's like that was a mystery cube. Because if you have a dot that doesn't exist, that makes a line that doesn't exist, that makes a plane that doesn't exist. You slap 6 non-existing planes together, you don't get existence. All you get is non-existence to the 4th. Okay? It's got nothing to do with existence. You just have got a bunch of non-existent dots together. So nothing exists. And that was not logical. And I have a tendency to be an extremely logical human being. And it turns out that Buckminster Fuller, I found out later, had the same problem at school. He wrote about it in his book. And he didn't understand how this worked neither, and he didn't thought it was correct. And actually, through my research, I found that this is an ancient riddle. It's mentioned in ancient manuscripts that are from the Middle East and so on, and there is all sorts of treaties about this problem, although this problem is the foundation of our understanding of physics and dimensions. And all of our knowledge is actually based on it. And it creates a lot of problems. This simple riddle that is unsolved has generated a whole set of distortion in our societies and in the way we do physics and the way we understand the universe and how we relate to it. And we're going to see that today. We're going to see this error just come back and bite us in the butt every time we come around the corner. You all following this?
Yeah.
Well, okay. Well, I was going home from my school that night, and, I had an hour and a half bus ride back home. And that's because I kept on getting kicked out of the schools closest to my home. So I had to go further and further, and some physicist once told me, actually, I was furthering my education that way. And I thought that was true because I had all this time to think when I was in the bus. So I was thinking, and I was going in this bus, and I'm like, I'm not living another day without solving this. I had no idea that nobody had been able to solve this or anything like that. Nobody told me it was not solvable. Nobody told me I shouldn't be working on this when I was 10. So I was in my bus going, I cannot survive another day on this planet without knowing what the heck a dimension is. And what is this dimension I'm in? And what are these other dimensions I'm experiencing, or these other energies I'm experiencing, and so on. So I'm thinking, and I'm thinking, and I'm thinking, and I've got a goal in my head that I'm going to solve this before I get off the bus. So I'm, the bus is getting crowdier, and, it's like more and more people in there, and it's getting really kind of tight. I'm like sitting on this little bench, and I'm getting squashed, and I'm getting really uncomfortable, and I'm trying to think about all this, and I'm like, I got to find a solution. And at one point I thought, well, maybe I should like try to get my mind out of this bus because it's just getting too crowded in here. So I started to expand my mind, and I rose above the bus, and I saw, in my mind's eye, I saw the bus becoming a dot. And then I rose further, and I saw the Earth becoming a dot. And I rose further, I saw the solar system becoming a dot. And I rose further, and I saw the galaxy becoming a dot. And then I flew back into the galaxy, into the solar system, and back into the, I saw the Earth, and then I saw the bus, and I found the bus, and flew back into my body. And I thought, wow. And I looked at my hand, and I went, I flew into my hand in my mind's eye, and I saw it was made out of dots. I didn't know those were called cells, And then I flew into one of the cells in my mind's eye, and I saw that cell had to be made of thousands of little dots we call atoms. And I flew into, actually, billions of little dots we call atoms. And then I flew into one of those dots, and I saw that inside the atom there was a whole bunch of other dots in the middle, and so on. And actually, that was my first glimpse at the fractal nature of the universe. And I thought, oh my God, I know how to solve this. It's a dot within a dot within a dot to infinity. And the only thing that exists is the dot. Within each point, all information is available. Each point contains the whole. So the only true existence is the point. And from that point, or from an arrangement of points, you get all of reality. Wow. I was onto something. I got really excited. It's like, that's the way it goes. Each point contains the whole. Each point has all information. Each point is connected to all other points in the universe. And then the universe arranges the points in all sorts of different ways and makes all of the things we see. Well, that would mean that each point had to contain infinite amount of energy, infinite amount of information. Well, I got excited, and I'm like, oh my God, I got to tell my mom. So I went back home, I got out of the bus, and I'm all excited. I'm like walking on the cloud. I'm feeling like I've got this illumination, and I'm on my way to changing the world and all this, and I get home and I wait for my mom. My mom comes back from work and I'm like, "Oh, Mom, I figured out something at school today. It's real important." She smiles and she's like, "Oh my God, he finally had an A in the test or something. She thought I did something real good at school." And I'm like, "Mom, I figured out that each point contains the whole. Each part of you has infinite involved in it, and each point has a connection to everything else." And I'm telling her all this, and she looked at me, and she, "Part of your curriculum at school, is it? And I think you should go back to it. You're not doing." And and my mom is kind of a pragmatic person, and she's a Roman Italian, woman, and she just looked at me and said, "Anyway, today I don't feel infinite." I'm not feeling infinite, so why don't you just go back to your curriculum, Go do your homework or something. And it I got disappointed. It crushed me. I was like, "Oh my God, she's right. How can a point contain the whole if a point has a finite boundary? If the body has a finite boundary, how can it have infinity in it?" So I was like, "Oh, I gotta go back to the drawing board on this one." I was like, that doesn't really work. How do I do this? Well, it turns out that that's gotta be one of the largest errors that is going on in our understanding of physics and our understanding of the way the universe functions and our place in it. That is, that infinity and finite system are opposites instead of complementary. But how can a finite system and an infinite curvature be complementary? How can the two be together? I knew when I was 10 that there was a solution to this, because I knew I was right, because I had seen it in my mind's eye. I instinctively knew it. Actually, most children I talk to, if they haven't gone through that first lesson of geometry, know this. They think of the universe as infinitely big and infinitely small, all embedded into each other to infinity. In general, they think of that as being quite logical. The kids are not the only people that thought of this. Do we have sound on the computer? One famous physicist, Carl Sagan, wrote a book called Contact. And then there was a movie that was made out of that book. And the movie starts like this. Thank you. Okay, this is a little bit hard to see. It's the edge of the Earth. There we go. And so we're moving away from the Earth in space. And as we move out, we catch up with all the radio waves that were sent into space by the Earth. So it's like almost going back in time. goes Saturn. Now we're exiting our solar system. And shortly we'll be exiting the arm of the galaxy we're in. Here's our galaxy center. And now we're moving faster and faster away from our galactic supercluster. So the concept of a universe within a point, was there quite definitely described. Let me tell you as well that the concept of a universe coming out of a dot is not that outrageous. The current theory of the Big Bang says that we all came out of a dot the size of a Planck's length, 10 to the minus 33 billions of times smaller than an atom, and all of our universe. The only difference here is that this view says, no, it didn't all emerge from one dot that decided to make a universe. All dots contain the possibility of a universe in it. All dots are connected to all other dots. And so here, then Hollywood came up with their version of this concept. And since they're the man in black, they have much faster technology. They can move much faster than anybody else. So that's the end of Man in Black movie. And they have extreme speed. Because they got all that alien technology. Little marbles we are. So these concepts have been around, except they've never really been understood because, again, how do you fit infinity in a finite space? And it's crucial that we understand how we did it. Well, when I grew up, eventually, I found the solution. I found the answer to this. The solution is what is called a fractal. And I'm going to show you very, very simply how infinity fits into finite. How infinity and finite systems are absolutely complementary. And that each point has the potential of having all information in it. I'm going to show you this in a geometrical way, so it's really easy to understand. And it just happens that the way I'm showing you this turns out to be very crucial to the way systems are organized and generate the geometry of our reality everywhere we look. So we're going to make a boundary, a circle, and inside it we're going to inscribe a tetrahedron, or an equilateral triangle in this case. The boundary could be a sphere, and the middle triangle could be a tetrahedron. Okay? So this you can visualize in 3D space, in spherical coordinates. Now, the universe is polarized, positive, negative, male, female, white and black. So this has a polarity, right? And generates a reverse equilateral triangle. Now, I'll give you a hint to the ancient civilization part of this lecture we're going to have today. Right away, we have one of the most commonly found symbols in all ancient civilization around the world. A circle with a double triangular polarity inside it, commonly referred as the Star of David, or the Shield of Solomon, the Star of Zion. It's found on the on many walls around the world of ancient civilization. Now, if you keep adding triangles, you get smaller stars of David. And then you can keep adding them again, and you get smaller stars again. Now, at each level of the fractal, you're going to generate a boundary. This is an important part to understand. Each level generates a boundary. Again, boundaries at the next level. And now I'm making smaller boundaries. See, I didn't put them all around because I got lazy. And then now I'm making smaller boundaries again. And smaller, and now they're so small you can't see it. Now, if I give that equation to my computer and got the computer to just keep making boundaries, keep making smaller and smaller triangles, it would continue to do this to infinity until it heated up, melt down, and I'd have to go and get myself a new computer. But assuming it didn't do that, it would keep making smaller and smaller triangles to infinity. And I could give it a code so that every 5 iteration or 6 iteration, it would zoom in so you could see it again, and then starts making more triangles, and then zoom in, and then so on to infinity. However, although I can place an infinite amount of triangles, I will never exceed the first boundary I made for myself. Never. I just showed you how infinity fits in a finite space, or a so-called finite space. Because you can divide to infinity within the circumference of a circle. What does that mean? Why is that important? What does that do to your life? What does that do to the way we do things on this planet? Well, let me give you an example, even if it's just for physics. We built faster and faster and faster accelerators that cost billions of dollars to build, to get smaller and smaller and smaller and smaller. Now we're at like millions of times smaller than an atom particle, actually. And we're building accelerators now in Geneva in Switzerland that are costing $300 billion, I believe. 5 countries had to get together to build it, right? To get even smaller particles. Well, if we understand this principle, we would understand very quickly that you can keep building larger accelerators and you can keep getting smaller and smaller particles. You can always keep dividing. So we would give up the search for some fundamental particle and that's going to end the search for particles, and we would start to understand that what we need to discover is the dynamics of the division, the dynamics of the quantization. You understand? Not, how far we can go into infinity. Just so that some physicist can put his name on it and get a Nobel Prize for a new particle. But further, what does it mean to you? It means that if this is true, every one of your atoms, every one of your cells has infinite potential in it, has infinite connectivity to everything else. That each one of your atoms is a mini black hole. Because if there is infinite amount of particles in it that can be divided, that means it has infinite mass. Most people say, I can't envision infinity. If, it's a good point. You might have to take a lot of coffee in the morning. But it's like, I can't visualize infinity. If it's true that I have an infinite nature inside of me, how is it that I can't see it, that I can't visualize it? That's a good point. Well, the reason is that most people try to envision infinitely large when they think of infinity. So that is limited by your senses because it's external to you. However, here we see that through infinite division, we can generate singularity, a link to all other things. So when you try to visualize infinity, you might want to turn your senses inwards and go towards the infinitely small that's contained in all of your atoms, in all of your cells. Well, just happens that all of the masters that have walked the earth have been trying to tell people about turning their senses inward through meditation, prayers, and so on, to connect with their infinite nature. The Buddha, Jesus, all these people said the temple of heaven is within you and within everything. That's the description of a fractal, my friend. The thing is that it was never appropriately applied to physics. It has huge repercussions in physics because it completely changes the way we look at the structure of reality if everything contains the whole. So you see already this is a key to understanding your nature and your potential. How many times in the year do you turn your senses inward and connect with your infinite nature? And so I was really excited about this because it seemed to say as well that the universe would be expanding and contracting, right? If everything goes towards infinity at the center of all atoms, then the universe is contracting as much as it expands. And I could see how the external part of my existence is the expansive part, and the internal part of my existence is the contractive part. So I started to think in those terms when I was actually 11, and I learned to meditate. A young master of meditation from India taught me to meditate. And I was really excited because I was discovering a whole world within myself that seemed to have infinite potential. So I started to spend more and more time concentrating inward and connecting with that part of my existence. And I started to think that there must be a balance between the expansion of the universe and the contraction of the universe. And the contractive part of that balance equation is the part that generates. And the radiating part is the part that alienates, that destroys. Yet, all of our science, all of the knowledge is based on the radiating part. There's nothing we've really discovered since fire. We explode everything. We put fuel in a rocket, right? Tons and tons of fuel, and we light the bottom, put a few people on top, and pray that they're going to survive the experience. That's our approach. We put fuel in our car, and we explode it in a chamber, and we push a piston up and down. It's all about explosion. And we think the universe is expanding. When much later, I was brought to Georgia Tech to have a conference, kind of a debate with other physicists. These are very well-known physicists, highly regarded, older people that had their students there. And we were talking about things. Some of the students were there. They came in and out. We were, looking at equations. We had all this stuff on the big wall there, on the blackboard. And I showed up with this book. This is the only book I had with me. I had maybe another few, but that was my main book. It's called Gravitation. It's a classical book about relativistic equations. It's written by Messner, Thorne, and Wheeler. Those are legends of physics. Wheeler having worked with Einstein and so on. And it's a brick, you can see. And that's why it's called gravitation. When you pick it up, you know everything you need to know about gravity. And I was going through all the equations, and I could see that the physicists were starting to get upset with me. I was, kind of going through, the way they think of the universal dynamics and the universal expansion and all this. And I finally said, okay, if I understand your model right, and I opened Gravitation on page 719, and I said, if this is correct, then the universe is something like this, which they show you after about 1,000 equations. The model for our universe is a balloon with pennies glued to it. So what you do is you take a balloon, you take a bunch of pennies, and a glue gun. And you glue the pennies to the balloon, and the pennies represent galaxies. And then as the balloon inflates, the galaxies move away from each other. generating the universal expansion we observe with the Hubble. It's called the Hubble constant, or the Hubble expansion, and is observed by various modalities, including telescopes. And so I'm going through this with them, and you got to realize these guys are very accomplished physicists, and they're looking at me going, "Oh my God, this is like kindergarten stuff. If you don't know this stuff, you should go back home and study a little more before you waste our time." And so I was like, well, what I want to know is where is the equation, because I really looked through all your stuff, and where is the equation for this guy? And, the room became quiet. And I was saying, well, this is definitely a component of the dynamics that are going on. And I said, if you keep drawing, if you don't stop at the face, and you keep drawing the rest of the guy, you'll notice that when the balloon expands, the lungs contract. For every action, there's an equal and opposite reaction. First law of physics. That hurt. Everybody had a blank look on their face, and the room became so quiet you could hear a pin drop. And I could see my dear friend and sponsor across the room going, "Oh, you're doing damage." Kind of obvious. Completely missed. Obviously, if the universe expands, then something is contracting. And that dynamic of expansion would be a feedback, right? Expand, contract, expand, contract. And it would have a very specific topological structure, meaning it would look in a very specific way. It would have very specific dynamics for things to be able to expand and then contract and so on. So, when you think about it, and I was thinking about it for years, if you radiate, if you look at the universe, you find that everything in the universe radiates. What does it radiate in? In the vacuum. The vacuum of space. Well then, the vacuum cannot be thought of as empty, can it? Because no energy is lost, no energy is gained. So if all the suns, all the stars, all the galaxies, all the black holes, everything we see radiates into the vacuum, then the vacuum must be full. Full of energy. And it was clear to me that then the vacuum must be the contractive side of the event horizon, the contractive side of the structure of reality, the part we don't see. Why? Because it's contracting towards infinity, moving away from us. It appears to us as vacuum. So I was puzzled about that, and I remembered my first class of physics. So again, you know, I'm all excited. Now I'm about 16, and I'm going to my first class of physics. Well, actually, I'm like 14 or, you know, 15, something like that. And I'm like, oh my God, today I'm going to go into my first class of physics. I'm going to learn everything there is to know about atoms and reality. So when I sat, the first thing I did is put my hand up, and, you know, the teacher didn't know me better at the time, so he asked me what I wanted. And I said, what is an atom? I was surprised to hear the response. I thought, oh, he's just going to spell it out. What the heck is an atom? And he said, oh, that's way too complex for a first physics lesson. And in fact, we are not quite sure what an atom is. I was like, huh? You mean that in all of the years of physics that have been going on this planet, you guys still don't know what the heck is an atom? How can you tell what anything else is then? Right? And so I was like puzzled, but one thing he said is that one thing we know is that the atom is made out of 99.99999% space. And I went, oh, space. Mostly space. Everything you see, everything you touch, everything is mostly space. 99.99999%. That includes you. You are 99.99999% space. And it was like, wait a minute. That the universe is connected by an unseen force, right? What would be the thing that would connect all things? Space. That's the only thing that's everywhere. And that's the only thing that all energy is radiated into. So I start to think, maybe it's the exact contrary. Maybe the atom is just a result of a division in space. Aha! Like the fractal structure we just saw. Divisions of space to infinity. Now it starts to look a little different, doesn't it? Is your brain starting to hurt? That's okay if it does. It's normal. Don't panic. It'll get better. But imagine you're doing music. You need silence to be able to cut it, to make music, to make a beat. If you're making reality, you need space to define the reality in between. So space, reality could be just various resolution, right? Various divisions of space in a fractal structured vacuum, which is some of the math we just published recently. It's becoming extremely popular, the concept of a structured vacuum, energetic structured vacuum. This is in advanced physics. So I dug a little bit more after that first class in physics, and I found something that blew my mind. Much later I did find it. And it says this. It's in gravitation. Present day quantum field theory gets rid by a renormalization process of an energy density in the vacuum that would formerly be infinite, if not if not removed by renormalization. Now people, you don't know what renormalization is. What they tried to do to me at school. It didn't work so good, can you tell? We'll talk about renormalization in a minute, but here, energy density in the vacuum that would formerly be infinite. That means that current day physics for subatomic particle, quantum physics, has to have a huge amount of energy in the vacuum for all their physics to work. Why do they try to remove it by renormalization? I'll explain that right now. There is two infinities in physics. That sounds like a misnomer, but that's the way it is. One infinity is infinitely small quantities. You know, you mix this quantity with this quantity and you approximate it, and you know, infinitely small. At one point you say, okay, well, it doesn't matter, it's just bits, you know, like infinitely small. It's okay, you can ignore infinitely small. And then there is another infinity. That one has a highly technical term that is found in physics books, and that term is nasty infinity. Yes, it's used in physics commonly. Nasty infinity is not infinitely small, but infinitely big. When you find something that's infinitely big, you can't just say, oh, I'm just going to ignore that. Right? I'm just going to ignore infinite amount of energy. I don't think so. You got to do something with it. And that's why they call it nasty, because it's like, oh my God, what do? We've got infinite amount of energy in the vacuum. You know, nobody's going to believe us. So there's a thing in physics is that if you find nasty infinity, you got to somehow get rid of it. And if you don't, then your theory is no good. It's discarded. And the way they came up with a way to get rid of it is that they use a renormalization process. Basically, they take the infinitely large number and they cut it. Okay? And then they try to shove it under the carpet somewhere, and they don't talk about it. So, basically, you can graduate with a PhD in physics and never have heard that the vacuum density is infinite at the Planck's distance. Right? It's called quantum fluctuation. Now it's getting more talked about because of many, many different reasons. But so it's becoming more popular in people. But only a few years ago, if you talk to people about, you know, infinite density in the vacuum, they'd look at you and go, oh my God, what are you talking about? They think you're talking about a vacuum chamber in a laboratory somewhere. So I was, you know, so how did they renormalize this? Well, they took a thing that's called a Planck's distance. And I'm not going to go into too much details on how they derived this number. But it has to do with the Schrödinger's equations. And the Planck distance is 1.616 multiplied by 10 to the minus 33. This is a small little dot. And basically they say this little dot is the smallest thing the universe does. Right? We'll make the dot. See? Here's my Planck's length. And they say the universe goes to that small and then stops. It's like, I'm done. I'm out of here. This is way small enough. I ain't doing nothing smaller. Okay. And then what they did is they went and see how many of these Planck's lengths, right, would fit in a centimeter cube of space, to try to renormalize the infinite density of the vacuum, to get a closed number. So they stacked the Planck's length into a centimeter cube of space, basically, and calculated that the density of the Planck's length would have to be 10 to the 94 grams per centimeter cube. 10 with 94 zeros of these Planck's length in a centimeter cube of space. Well, now they had a finite number. But what is that finite number? Let me give you an idea. If you took all the stars we observe in the universe with the largest telescope on Earth, actually off the Earth, the Hubble, and you stuck, and we see 100 billion galaxies. Each galaxy has over 300 billion stars in it. Most of these stars larger than our solar system. Okay? And you took all that stuff with a huge trash compactor and you squashed it into a centimeter cube of space, you still would not have 10 to the 94 grams per centimeter cube of density. You'd still be short. Okay, so you guys got a finite number. It sounds pretty infinite to me. Maybe we should learn to deal with infinities instead of trying to renormalize them. Because, you know, people got Nobel Prizes for this. So 10 to the 94 grams per centimeter cube is actually what's called the vacuum fluctuation density in quantum space. Meaning that the vacuum is not empty. It's extremely dense. But why does it feel like the vacuum then? It doesn't feel so dense either after, you know, a night at Burning Man. With what happens there, you know, how can the vacuum be so dense? Well, if the vacuum is everywhere and infinite in nature, then it's in perfect equilibrium. And if it's in perfect equilibrium, there's no way you're going to feel it. It can have infinite forces in it, but if it's in perfect equilibrium, you're not going to know it's there. Just like a fish inside the ocean, in the water, will never know it's in the water until you take him out of the water and it feels a different density. We have no way to feel a different vacuum. So we think of the vacuum as empty, when actually it's full. And you can come to those conclusions yourself by simply realizing that if everything is radiating in the vacuum cannot be empty. So I was amazed, and I'm like, okay, well, let's go with this. The universe is expanding. The vacuum is contracting to infinity. And all of reality emerged from the feedback between expansion and contraction. It becomes really clear then that the expansion part would be the electromagnetic radiation part of the universe, and the contractive part would be the curvature of space-time and the vacuum energy going towards singularity at the center of the system. So, yeah, I'm going to elaborate on it. It became really clear, well, basically, that if there is an expansive and a contractive part of the universe, the expansion part is what we see as reality, which is the radiating electromagnetic emission that we see. A star, a planet, an atom, all radiate energy. That's why we see it, right? And the contractive part that we don't see would be the vacuum energy curving, space-time curving into it, generating singularity, generating the gravitational field. So now I had an inkling about the relationship between electromagnetism, radiation, and gravity.
Gravity goes into the singularity.
Gravity going towards singularity. Space-time curving towards singularity. Now, I later realized that that wasn't that outrageous of a thought. Because when Einstein wrote his field equations, he didn't solve them. Einstein just wrote the expressions. It's 10 differential equations. He couldn't solve them. A physicist that was fighting on the Russian front, right, while dodging bullets, was working hard at solving those equations after they were published. His name was Karl Schwarzschild. And he generated what's called the Schwarzschild solution. As soon as he solved Einstein's field equation, he sent a paper to Einstein with the results. And Einstein presented it to the German Academy of Science, and it became the first solution to Einstein's field equation, which we still use today. Karl Schwarzschild died 2 weeks later on the front and never had time to give further complexity to his solution. Basically, he did it without rotating the field. At first, he was trying to estimate, so he didn't have a rotating metric. And we'll see a little bit more about that later. But the first solution to Einstein's field equation was a black hole. It's called a Schwarzschild singularity. It made a black hole. But because when you go towards singularity with Einstein's field equations, they go to infinity, nasty infinity, that part is ignored. It's called the unsolved nonlinear part of Einstein's field equation. So we use only the weak part of the gravitational field. The part that's not curving very much towards singularity. The part that's much weaker on the outside of singularity. You guys see where I'm going with this? Oh my God. big omission. Infinite amount of singularities just scrapped because it didn't fit our concepts. So I started to think, well, okay, if the universe is expanding and the universe is contracting, then there's got to be geometry to describe that. There's got to be a structure that describes the contractive side. The expansion side was pretty easy to figure out. If things are expanding from a point, from a center, then they must be expanding radially. It must make the geometry of a sphere. Right? The expansive part being the geometry of a sphere. That's what we see. A sun, a planet, a galaxy. Galaxies have galactic halos that are perfect spheres around them. Atoms, cells, whatever. Spheres. So we see the sphere part because that's the expansion part. But what I wanted to know about was the contractive structure of the vacuum. Why did I want to know about that? Because if I understood the structure of the contractive part of the vacuum, then I understood the geometry of the foundation of creation. Do you guys follow me there? Because if that's what creates, if that's the general active thing, that's the thing that holds things together, then that's the key to the force of creation of all things. If you have a sphere or a ball on the end of a rope and you spin the rope, you're going to feel a force outside pulling away from your hand, right? That is not a true force. It's called centrifugal force. It's not a true force because the only reason that force is occurring is because the ball is attached to the rope, which is attached to your hand. The centripetal force, the force that's holding the ball to the center, is what's making it go in a circle. Without the string, the ball is going straight and there's no force. You guys follow me? So actually the force that holds to the center is the primary force from which the illusionary radiation occurs. Do you see what I'm saying? I mean, that has huge implication in philosophy as well. Because if you go inward deeper and deeper, then you would expect more and more radiance to occur. Because you have a feedback relationship between the internal gravitational collapse and the external expansion of the electromagnetic field. So I was really excited about that, but I didn't know what was the geometry or the structure of the collapse. I knew one thing, is that the geometry of the collapse had to be in equilibrium. So I looked and I thought, well, if the sphere is the highest volume possible, which it is, then the geometry, so it's the highest volume possible because it's expanding, right? Then the geometry of the collapsing vacuum must be the smallest geometry possible. The smallest volume, the volume that's collapsing. And that is a tetrahedron. Everybody here knows what a tetrahedron is? Okay. While I'm traveling, it's kind of hard to bring all my models. But this is a double tetrahedron. Okay, there's two there. Actually, there's 8 making an octahedron in the middle, but we're not going to get too complex here. If you have a tetrahedron, you have 4 faces, 4 equilateral triangle faces. It's like a pyramid with a triangle base. Okay? It's like 3 triangle faces with a triangle base. It's the smallest volume possible. And thus, that had to be the final geometry of the collapse. Well, you know, when I was thinking about these things, it was almost 15 years ago, there wasn't people like if you go in Sedona right now, you know, like, or, you know, Burning Man or whatever, you know, there wasn't people going around with tetrahedrons on their heads and like living in tetrahedron houses and, you know, having tetrahedron cars and stuff like that. You know, at that time, nobody even knew what the heck was a tetrahedron. I mean, it was not so common, although, you know, that comes all the way back from the Pythagorean school and then Plato schools and so on. So I was, you know, at the age of 16, after all my encounters with current physics and so on, I decided I was done. And it's great because I just went to the Einstein exhibit in New York and found out that Einstein did the exact same thing and quit school at 16. But I was, you know, I couldn't keep doing this. I was just running into troubles everywhere I went. And so I started to teach skiing. Because I was a good skier, I figured I can live that way and do research at night. So I was doing research at night and skiing every day, teaching skiing, being in nature. And I was like, well, you know, after years of skiing, I taught skiing for 15 years. I became one of the top ski instructors in Canada. I was one of the 20 top ski instructor in Canada, ski coach. And I was very successful. And I was going from Canada to Australia, New Zealand in the summer to do their ski season there. And then back to Canada, and then back to Australia, and then back to Canada. And I was freezing my butts out. I had no time to unfreeze. I had like a week and a half to 2 weeks on, you know, Fiji Island, you know, in between seasons. And I was just not cutting it. So after a while of doing that, I got tired of it. And one summer I said, that's it. I ain't teaching skiing again this summer. I'm going to teach scuba diving. So I'm, you know, decided to thaw out one summer and teach scuba diving. And I had been scuba diving since I was a young kid. So I knew I could teach scuba diving. So I opened a map and I thought, okay, I got to be south of the border. It's got to be extremely hot. And so I took a map of Mexico, and I found this little island called Isla Mujeres. And I thought, wow, you know, I was a ski instructor, island of the women, man. That sounds good to me. So I decided I was going to go to Isla Mujeres. So I went down there, and I got a job as a dive master, and I started to, you know, dive master down there, and I learned a lot and all this. And then one day, I had a day off, and I decided to go for a little expedition. And I hadn't seen the pyramids, so I decided to go to Chichen Itza, the pyramids of Chichen Itza. Well, you know, it's like you get in the bus, you know, I had to take the ferry from the island. I got in the bus, you know, with the chickens and the pigs and everything. And I'm going through the jungle, you know, for hours. And then finally, you see these pyramids sticking out of the jungle in the middle of nowhere. And it's like, huh? And they're like these huge monuments. And I get onto the site, and I'm walking around, and I'm like going, wow, how did this get here? So I'm climbing on top of the pyramid, and I figure I meditate on it, so I'm sitting down, I'm trying to meditate, and sure enough, as soon as I close my eyes, I hear, a group of tourists coming off the stairs on the other side with a tour guide. I'm like listening, trying to meditate, and and I'm listening to this tour guide, and the tour guide is saying how, all the rocks were cut in the quarry over the mountain range we see in the distance, and that they were carried from there, cut with copper tools, and then carried from there on with vine ropes on logs across the mountains, across the jungle, down the mountains into Chichen Itza, and then assembled into this amazing monument we were standing on. I'm listening to this, and I'm going, really? And then he mentioned that actually the monument was actually carved and cut perfectly so that on the solstice every year, when the sun rises, it casts a shadow of a snake going up the stairways, and the snake head is carved on the bottom, and it really works. And I'm listening to this, and I'm like, wait a minute, that doesn't sound right. These people, like thousands of years ago, were going around with huge stones across jungle, across mountain range, right? And like putting them in this perfect building that's amazingly well aligned to astronomical events. And it's not like you can build the pyramid and then like get Joe out there and get, okay Joe, the sun is rising now. Okay, pick it up now. Okay, a little bit to the left. You can't do that. You gotta calculate that stuff in advance. And those are not simple calculations. Those are very complex. Just happens that most of these buildings we find around the world are pyramidal. Most of these enigmatic buildings are pyramidal, and most of them are aligned with incredible accuracy to astronomical events. So as I was listening to this, and I'm a climber as well, and I know rock, and I know that you can't cut rock with copper. And I find out later on that archaeologists say, oh well, they had a way to temper the copper so it became hard. And I was like, okay, can anybody else do that? No. You mean that with all the millions of dollars that are invested in research in metallurgy, nobody is able to harden copper, but the ancient people thousands of years ago could do it? The other thing is that, have you ever tried to pull rocks on logs in the jungle with vine ropes? And now, you're talking about people that didn't have the pulley. So now you got to stack these rocks to make your pyramid without a pulley. That didn't sound right to me. Just because I'm a type of a logical person. And I was standing on top of this pyramid, kind of scratching my head, going, oh my God, that doesn't sound right. There's got to be some mystery we're missing here. And then it hit me. It's like, wait a minute. This is a pyramid. And there's pyramids all around the world from these ancient civilizations. Why were they all building the exact same geometry? Why didn't they make a cube? What's going on? What's with this pyramidal thing? And I thought, okay, maybe this is a long shot, but maybe they knew something about the fundamental structure of the vacuum. Maybe they knew something about the logos of reality, the fundamental structure from which everything emerges. And maybe pyramids are involved in that. So when I got back home, at the time I lived at Whistler, Canada, a big ski hill, I went to my local library. Well, you know, in a ski resort, library is not, you know, so elaborate. But I was looking for information about ancient civilization, and the first book I came across was titled Mystery of the Mexican Pyramid by Peter Tompkins. And I thought, oh, that's a good title. Definitely is a mystery there. And I opened it randomly, if there is such a thing. And when I did, this graphic, this is not my graphic, this graphic was on the page. A tetrahedron within a sphere. Well, I had spent by then a very long time coming up with the idea that a tetrahedron and a sphere must be part of the geometry of reality. And it was the base of my theory. And to find this in a book that talked about ancient knowledge was crazy. I'm like, oh my God, they beat me to it by 2,000 years. Dang, I was going to copyright this. And I was like, oh, what's that doing there? And, you know, there was a whole elaboration about the relationship of a tetrahedron to a sphere, showing that a tetrahedron has a very interesting relationship to the sphere, where it intersects the sphere at exactly 2/3 down, 1/3 up, if one point is on the south, or if one point is on the north, then 2/3 up and 1/3 down. And it intersects the sphere at exactly 19.471222064 latitude, which is exactly where I live, actually. I live on the big island of Hawaii, and that is on one of those points. And I was puzzled. How did that get in there? Did somebody listen to my thoughts? But I realized that this graphic was the result of a paper that had been published by an American engineer that had been hired to survey the huge city, ancient city of Teotihuacan near Mexico City. This is where there's the moon pyramid and the sun pyramid and the way of the dead and all this stuff. His name was Hugh Holliston Jr., and the paper was published by the American Health Society after 20 years of him putting, surveying all of the buildings there. Well, when Hugh Holliston Jr. started to survey the buildings at that ancient city, he found something very bizarre. He found that all the buildings there seems to, like the large buildings, the temples and such, seems to be in the exact appropriate place to describe all the orbits of our solar system, with the sun pyramid, the moon pyramid, and everything. He found all the orbits, including Pluto and Neptune. Now, Pluto and Neptune, Neptune, I think it was late 1800s. Pluto was discovered by us early 1900s, 1920-something, by the observatory in Arizona there, in Flagstaff, Arizona. So how come these people thousands of years ago had these orbitals? Not only did they know these planets were there, but it had the appropriate placement to generate their orbits. Those are extremely difficult things to figure out, especially if you can't see it. And so that blew his mind. And he started to continue to investigate, and he found that there was some incredible mathematical recurrence in all of the measurements that he was taking. And that recurrence, these mathematics that kept on creeping up, were always the same. And he figured out that they were pointing out to the mathematics of a sphere and a tetrahedron embedded in it. And that's why he put that graphic in his paper, saying that if these people were trying to communicate something to us, they were trying to tell us about a sphere and a tetrahedron. He didn't notice, though, that even that city, right beside Mexico City, that ancient city, is exactly at 19.47 latitude on the Earth as well. So not only does it have the mathematics of a tetrahedron in a sphere in all of its layouts, but as well it is placed on the Earth exactly where a tetrahedron would intersect a sphere.
What's the third point?
Well, this is a grand circle, all around the Earth. So depending on where you put this point, these other points will move, right? But if you put this point at the big island of Hawaii, then Mexico City is somewhere in the middle here, in between these 2 points. This one is near the coast of Africa, I believe, and then this one is India. The Daikini temples in India. And so I was amazed that this engineer had come up with this. And I was confirming, that imagine that there is a fundamental structure to the vacuum, that there is a fundamental structure to reality. You would expect that throughout the ages, we would have come up with it, because it would be inherent in us. It would be oozing out of us. So I thought, maybe they came up with this then. But I knew there was something wrong, because a tetrahedron on its own is not in equilibrium. And I knew the vacuum geometry had to be in perfect equilibrium. So I had to find something else. Well, at the end of his essay, Hugh Holliston Jr. mentioned a very important thing: the isotropic vector metric from Buckminster Fuller. He said that the mathematical constant that he got from his surveying of that ancient city pointed out to the square root of 9/8, which is the mathematical constant for an isotropic vector metric generated by Buckminster Fuller. Bucky thought that this metric was the fundamental mathematical blueprint of the universe. Well, Bucky was quite eccentric. However, many of the things that Bucky came up with were later confirmed. So he's getting more and more acceptance of his work, although he's not around to appreciate it anymore. But the blueprint of the universe, he thought, was the isotropic vector metric. What is this thing? It's 10 tetrahedron on the bottom. This is called a 4-frequency isotropic vector metric. So 10 tetrahedrons on the bottom, 3 in the middle, I'm sorry, 6 in the middle, 3 on top, and then 1, making a huge tetrahedron on its own. Can everybody see this? So there's actually 20 tetrahedron in an isotropic vector metric. And if you take only one face of the isotropic vector metric, right, just a plane of it, then you have 4 faces on the bottom, 3 faces on the second level, 2 faces on the third level, and 1 face on top. Everybody sees this? Okay. Well, when I found the isotropic vector metric, I thought, well, I'm interested about negative space. So let me take off the tetrahedrons and see what's in between them. So I did that, and when I did that, I realized what was in between the tetrahedrons. They're octahedrons. Do I have a little octahedron somewhere? Oh, I don't. I guess it got destroyed. The glue, while I was traveling, melted with this 108-degree heat we've been having. So I lost some of my models. But an octahedron is a pyramid with another one below it. Emphasis on the word pyramid. So I was happy to find that the pyramidal geometry was present between the tetrahedrons. Can everybody see how an octahedron is 2 pyramids base to base? If this is one point of the pyramid, then the base is here, and it's a square base. It looks rectangular because it's in perspective. And the other point is here, right? 2 pyramids base to base. There is a bunch of them together, but when I did this, I realized there was something weird. There was something weird in the middle of the metric, because the metric is called isotropic. So you would expect that it would be always in balance, that it would always be in symmetry. But there was this symmetry in the middle. I found 4 reverse tetrahedrons pointing down and rotated 180 degrees. And they didn't belong to the octahedron, and they didn't belong to the tetrahedrons that made up the outside or the metric. So there was a bunch of these, there was 4 of these tetrahedrons completely out of place, creating a symmetry in the middle of symmetry. Now I knew this had to be incomplete, because if this was the fundamental structure of the vacuum, it had to be isotropic and symmetric so that you would have perfect equilibrium. Oh, there's an octahedron. Thank you. Ooh, nice. Q-tips. Thank you. Appreciate. Q-tips with what? Honey?
Rubber cement.
Rubber cement. Here's an octahedron. And so when, yeah, that wouldn't melt as well. Oh, that's good. Because I used to do it with marshmallows, but then people would grab the marshmallows and eat them. And I lose my model. But anyway, so the isotropic vector metric had to be modified. I didn't know how. One thing I was sure of is that the universe is polarized, so that it had to be 2. Okay? Now, if you have a polarized universe, and you have 2 isotropic vector metrics, and they're mirroring each other, you have a problem. Because the two mirroring each other, base to base, don't make a sphere. Remember, fundamental axiom, the universe is generating spheres, right? So you don't have a sphere, you have an egg. And so now I had the chicken and an egg problem. And I was like, oh my God, what do I do with this? I didn't know what to do. But I knew it had to be two isotropic vector metric. I didn't know what to do with these other spaces, these other tetrahedrons in the middle, neither. And you got to realize that at that point in my evolution now, I'm finishing my ski career. I got a bunch of universal 2x4s behind the head, forcing me out, telling me you got to do this full time. You ain't gonna do this while teaching skiing. And this point, I'm still doing all this without a computer. So I'm rendering these geometries in my head, and I'm trying to figure out how they fit together. Okay, I found the octahedrons in the middle and all this, and then I'm going, okay, wait a minute, I gotta make this become a sphere. But I don't want to distort the geometry of the isotropic vector metric. It has to be tetrahedrons. So I'm like getting all frustrated about it, and I'm, okay, well finally I decided, okay, and I pushed one into the other, and I generated this in my brain. I was pushing one into the other and trying to figure out where the tetrahedrons would fall. And then that's when I realized what had happened. When you push one isotropic vector metric into the other so that you generate a perfect sphere, then the central geometry is a vector equilibrium, the only geometry in full equilibrium in all vectorial possibility. And there is no distortion because those four tetrahedrons that were in the isotropic vector matrix alone were there to accept the reverse one, so that the one isotropic vector metric was missing its better half. And when the two came together, it created equilibrium. I still get the chills from that time when I discovered this. It was like, oh my God, this is beautifully, metaphorically, and beautiful for what I'm trying to achieve. The geometry of equilibrium, the geometry of the vacuum. And I could see how the male and the females coming together generates a new point of center, a new being. Boy, that, at that point, I was living in my van. I had sold everything, all my ski equipment, all my stuff. I moved into a van so I could sponsor my research. And I moved down south so I wouldn't have to eat so much. And so I was doing this in my van, and I was so excited. I mean, this was better than sex. I mean, I didn't have a girlfriend at the time, And so it was just beautiful. It was metaphorically beautiful, but in the physics of what I was trying to achieve, it was exactly going in the direction I wanted it to go. And I realized that the vector equilibrium had to be fundamental to the structure of space, of the collapse. Why is the vector equilibrium the only geometry in full equilibrium in all vectorial possibility? Let me show you. If you have a vector going in one direction, and that vector has a certain length, we'll call the length of the vector its force. So longer it is, stronger it is, shorter it is, weaker it is. Okay? In order to get equilibrium, you would have to have a vector in the exact opposite direction with exactly the same length. But that's a weak equilibrium because you'd have to nail that vector so that it would be a perfect alignment here. Otherwise you would miss equilibrium, and any forces pushing down in any other direction would break the equilibrium. It's very precarious. So how would you increase stability? You'd probably add vectors at 90-degree angle from those. Now you increase equilibrium, right? However, the edge of your geometry has longer vectors than the vectors to the center. Because they're longer, they're stronger, and thus your geometry explodes. It doesn't work. What would you do to try to correct it? Probably add vectors at 45-degree angles from these other ones. But if you did that, then the edge vectors are shorter than the vectors to the center. The geometry implodes. You still don't have equilibrium. So what's the solution? The solution is the hexagon. Because the hexagon has edge vectors that are the exact same length as the vectors to the center. It's the only geometry that does that. So now you have equilibrium. And what does that look like in 3D? It looks like a vector equilibrium. This geometry here. Oh. Okay. Vector equilibrium. It's 8 tetrahedrons pointing inwards. Now, this can be seen as well as 4 hexagons intersecting each other. Do you see that? The red one on the edge, there's a blue one at the equator, and then 2 ones intersecting in the middle. Everybody see that? There's a red one on the edge, an hexagon on the edge. 4 hexagons intersecting, creating equilibrium at the center or singularity. And note that there is 12 vectors radiating from the vector equilibrium. So there's 12 vectors radiating from the center, and there's 12 edge vectors, 24 vectors. These numbers are found in most ancient civilization texts. 12, 24, and so on are found everywhere. The 12 angels with singularity in the middle, the 12 apostles with Emmanuel in the middle, the singularity, and so on. The 24 elders in Kabbalistic tradition, and so on. So I was really amazed that I had found this, but my geometry was still out of equilibrium. Meaning, on this geometry of the 2 isotropic vector metric, the vector equilibrium in the middle had all of its octahedrons filled. That means that when the vector equilibrium is in the middle, the pyramidal structures are completed with octahedrons. But the edge octahedrons were incomplete. So I still had a symmetry. So I went back to the drawing board, back in my van, trying to, I've got this in my brain, and I'm noticing that some of the faces of the octahedrons are not covered. So it's asymmetric. So I decided I have to keep adding tetrahedrons till I gain symmetry. So I kept on adding tetrahedrons, and to cover all of the faces, I had to add 24 tetrahedrons to the ones that were already there. So this is one isotropic vector metric is 20. The other one is 20, that's 40, plus 24. 40 plus 24 was 64 tetrahedron metric. The 64 tetrahedron metric is a match to many, many things. I'm going to give you a hint. There's 64 codons that generate the 20 amino acids of your DNA structure. Okay? Now, when I found the 64 tetrahedron grid, then I realized that that was the quanta in which symmetry was present everywhere, and equilibrium was truly generated at the center. But what got me really excited is that I realized what I had built. What I had built was a fractal structure, just like the 2D fractal structure I showed you at the beginning, but this one in full 3D spherical coordinates. The only true fractal 3D spherical coordinate that you will find. Can everybody see the vector equilibrium on the inside and then the vector equilibrium on the outside? This continues to grow to infinity. And I could see that the inside vector equilibrium, its radius is exactly half the radius of the one on the outside. So the geometry grows in fractals, but not only does it grow in fractals, the fractals are perfect octaves. You see? And so I got really excited. It's like, oh my God, here it is. The structure of the vacuum. Equilibrium to infinity. Infinitely big to infinitely small. And then I noticed further that how this was constructed is constructed this way. Let me see if I can let go of some of the stuff. Actually, I'm going to leave that. I realized what I had built. I had built a matrix based on 8 star tetrahedrons, each having 8 tetrahedron in it. Okay? All coming together towards the center to generate the star, the 64 tetrahedron grid. But when it did, the 8 stars coming together, okay, here you're only going to see 6, plus the one in front, and then there's one in the back you won't see. So the 8 stars coming together generate the vector equilibrium in the middle. Why is this significant? 8 star tetrahedron is made out of 8 tetrahedron pointing outward, radiation, coming together to generate the vector equilibrium, which is 8 tetrahedron coming towards the center, generating contraction. So now, not only did I have found the geometry of equilibrium, but I had found the only fractal 3D metric, and it generated expansion and contraction. Exactly all the axioms I had placed for myself when I started this investigation of the geometry of space. I was so excited. I'm still excited. I was doing this in my brain. I didn't have a computer, and I confirmed it later on computers. But I was like, oh my God, this is so awesome. And then something really weird happened. I knew I had the fundamental structure of space. I knew, I was definitely seeing. Now realize, you guys, if we truly have the fundamental structure of creation, then technology that's based on this information is going to tap directly into an infinite potential of energy, infinite potential of gravity, infinite potential of rejuvenation, regeneration, and so on. You're talking serious change in our way of doing technology. So I was really excited. And then a bunch of people in England called croppies. Those are people that measure and photograph crop circles. Okay? Now, I know you guys, crop circles, There's scientific papers that were just published in peer-reviewed journals about crop circles, because many of them are not being able to be explained by people going in the fields at night and stomping around, Doug and Dave drinking moonshine and freaking everybody out. Some of them are not easily explained, and actually papers have just been published in peer-reviewed journals saying that this might be a new source of energy. But the croppies that I'm talking about decided in 1997 that if somebody is trying to talk to us through the crop circles, maybe we should talk back. So they went in the crop circles and they wrote in big letters by stomping around with their boots, what do we need to know? Good question. And the next crop circle that occurred was the largest crop circle to date at that time. And it's this one. Have we seen this somewhere? This is everything we've been talking about this morning. What do we need to know? Well, that's really nice. They give us this. They even made it in a way that's not reproducible by Doug and Dave drinking moonshine. Because all the hay is woven in a way that it makes effects of light and shadow that gives the vertices, the edges of 3D tetrahedrons. That is not easily done in the middle of the night. And so, and it was enormous. It was the largest today. It was much larger than anything previous to that. And it was interestingly situated near ancient, sacred site. And then a few weeks later, the next crop circle, a few weeks later, was another iteration of the same thing. So they were insisting on the pattern. What do we need to know? You guys get it? Look at tetrahedral fractal geometry. Right? How do you fit infinity in a finite space? Note that on these fractal curves, although there's not a boundary around the whole thing, the boundary is implied because the circles are all there of the smaller boundaries of the fractal. You guys follow this? So I was like, oh my God. Well, when I found this, I was living at my friend Gabrielle Cousin, in Arizona, and he found me jumping on his couch